Okay. All right. So we already did the PowerPoint on this. You've seen a lot of examples. And now we're just going to do these top two problems for now. Okay? So what we're working on here, on this side, we're working on inelastic. Okay? And on the other side, we're working on elastic. Okay, so conservation of momentum, situation 2. Situation 1 was the explosions, okay, where the masses were combined and then separated. So here the masses are going to be separate and they're going to hit and then they're going to be combined. Okay, so it's basically the opposite of an explosion. Things hitting and sticking. Momentum is, what do you think? Always. Momentum is cool. No. Okay, momentum is always conserved, but in this situation, kinetic energy is not.
I didn't agree to have it, sorry.
That's okay. Kinetic energy is not conserved. All right. This right here. This is the definition of what makes it inelastic. When kinetic energy is not conserved, that means it's inelastic. Okay? Alright, so let's deal with this. A 10,000 kilogram railroad car is traveling 24 meters per second, and it strikes an identical car at rest. If the cars lock together, what is their common speed afterward? Let's draw a little picture. You are going to test this out in lab too, because we have those cars that can run and stick together with Velcro, right? So that's what we're going to do the next couple days. There's train car 1, and we'll just put its mass right on the side. 10,000 kilograms. And there's car 2. It's also 10,000. And this one has got a velocity vector before the collision, 24 meters per second. Okay, so we want to come up with a general equation here for this type of collision. And this, let's say v equals 0 initially for this one. Alright, so let's say this is a test or something, and you want to show as much work as possible so you can score as many points as possible. First thing you want to say is PI equals PF. And if I'm grading this, you're going to get 1 point just for saying that. Because you're showing me that, oh, I know that conservation of momentum applies here. Okay, so if you put that, it's automatically 1 point for collisions and explosions. Alright, so initially the masses are separate, so we're going to say M1 V1 plus M2 V2. Not R2D2. Okay, this is car 1 and car 2. And they're separate initially. Okay? This all right here is PI. That's the total momentum of the system. This one won't always be at rest. Sometimes they'll be moving towards each other like that and collide and stick together. Sometimes this one might be going slow in this direction and this one catches up and runs into it. Okay? But in this situation, this whole term we can cross out and put a 0. Starts from rest. Alright, now on the other side, we're going to use parentheses, and we're going to add the masses. This is showing that they stick together. We now consider the system one combined mass. And we could call this V final. We could call it V3. We could call it whatever we want. Velocity of the system if you wanted to. Alright. And now we simply have to plug in some numbers. So M1 is 1,000. Oh, thanks. Okay, 10,000. And then it's going 24 meters per second. And then over here, we have a total of 20,000. And we're going to try and get that V final. Okay, and you probably don't need your calculator for this because, check it out, I doubled the mass of the system, so what should happen to the velocity? It's going to be half of what it was. So 10,000 over 20,000 is a half. So I've got a half of 24. So V final equals 12 meters per second.
You actually do math.
Punch it in. Well, 10,000 over 20. I just divided the 20,000 to the other side.
But why are you saying, since you doubled that, half the other side?
Well, that's how the collision works. If the thing is getting twice as massive, to keep momentum the same, doesn't the velocity have to go down by a factor of 2?
Well, right, I understand that, but couldn't you just multiply 10,000 by 24 and divide that by 24?
Yep,
So you just-
and then I just did it in my head. Right. Okay. All right, going on to this one. Okay, this is connected to this right here. All right, and this basically is asking us to prove that the collision is inelastic. Okay, you guys with me on this one?
Yeah.
So to prove that it's inelastic, we have to look at the kinetic energy. Okay, so let's check this out. For the completely inelastic collision of two railroad cars, we consider in example 3, calculate how much of the initial KE is transformed into thermal and other forms of energy. So when these hit each other, you're going to hear that, right? That's lost energy. Okay, because of that it makes sound. What else is going to happen?
You're going to get hot.
Heat, friction, okay, all that stuff. That's going to be lost energy. We can figure out how much energy is lost by looking at this. So here's how we do it. We say KE initial, and we say KE final, and we calculate them both. And then we're going to compare them. Okay? So, KE is 1/2 mv squared. Initially, we have two separate masses. So let's just look at this one first. We've got 1/2 of 10,000 times 24 squared. Okay, but we've got to look at the kinetic energy of both masses. Okay, but this is easy, right? What's the kinetic energy of this one? 0. Okay, so we're just going to punch this into our calculators. All right, so let's do that. Okay, so half of 10,000 is 5,000. Okay, we'll square the 24. And we're going to get 2,880,000. So I'm going to say 2.88 times 10 is that right? To the 6th. Yep. Okay, what's the unit? That's going to be energy, so it's in joules. Okay, if it was force, it'd be in newtons. If you're not friends with scientific notation yet, you can write it all the way out, yes. Okay. All right, KE final. Let's check this one out. Final meaning after the collision. Okay, so when these have stuck together, we're dealing with one mass. So we're going to do 1/2 times the total 20,000. And we found out that the velocity was 12. So we're going to use that data here. And let's figure out how many joules are left over. So we're going to do 10,000 times 144, which is 12 squared. And what do we get? 1.44 times 10 to the 6th. Okay, so the system had this much kinetic energy, but then it lost a bunch. This is how much it has after the collision. Okay, so how do we find out how much was lost? We want to find the transform. So we're just going to we're going to subtract right there, and we're going to get 1.44 times 10 to the 6 joules lost. Yep, it lost half of its energy. Okay. All right, so there's a couple inelastic collisions there.